Today we're going to be talking about how to separate individual volatile organic compounds in a mixture. Volatile organic compounds, or VOCs, are defined as groups of carbon-based chemicals that easily evaporate at room temperature due to their relatively low boiling points. VOCs are a common indoor and outdoor air pollutant that have numerous adverse environmental and health effects, from the creation of ground-level ozone to causing cancer in humans and animals. This is why being able to test for such harmful compounds is so important. One of the many ways to separate these toxic chemicals for further analysis is through gas chromatography. The GalMac gas chromatograph, or GC, is an instrument that quickly separates and quantifies small amounts of pure individual compounds of high volatility within a mixture. The GC can only separate compounds and does not identify unknown compounds. A GC is composed of an injector port where the sample is inserted, two columns containing polar and nonpolar stationary phases, and a detector to measure the individual compounds. The injector port, columns, and detector are heated by a coil column in order to keep the compounds vaporized as they travel through the column. The polar column contains a polar stationary phase made of carbowax 20M, while the nonpolar column contains a nonpolar stationary phase composed of DC200. As the compounds move through the GC column, they travel between the stationary phase, where they stop and interact, and the mobile phase, composed of a gas, usually helium, that acts to both purify the compounds and transport them through the column. There are a number of factors that affect retention time of compounds. For example, the more volatile a compound, the faster it will elute due to its lower boiling point. In fact, compounds must have boiling points below 150 degrees Celsius in order to be separated by the GC. The polarity of a compound and its column also affect the retention rate. Depending on the type of the stationary phase in the column, polar or nonpolar, the polarity of the compounds in the mixture, each compound will elute at different rates. For example, a polar compound in the polar column will have a slower retention rate than the nonpolar compound in the same column because this polar compound interacts more strongly with the polar stationary phase. Flow rate is another factor that affects elution time. The higher the flow rate, the quicker the compounds are eluted as the carrier gas pushes them through the column. There are many other factors that have an effect on retention time, and each factor does not necessarily affect the compound in the same way or with the same magnitude. Instead, factors are dependent on one another, and some may take precedent over others. For example, compound A has a lower boiling point than compound B, so naturally you would expect compound A to elute first. However, compound A is more polar, so when both compounds are placed into the polar column, compound B actually elutes first.
Now we will discuss how to run and analyze samples in the GC. Here are a list of materials you will need for your lab. A bubble flow meter, a stopwatch, a syringe, a 25 milliliter Erlenmeyer flask with acetone for rinsing your syringe, and your compounds. Here are a list of compounds to choose from: acetone, benzene, isopropyl alcohol, methylene chloride, toluene, xylene, methanol, and ethanol. All of these compounds have boiling points lower than 150 degrees Celsius and are not too polar or nonpolar that they would take too long to pass through the column. You may want to cork your flask, as these are volatile compounds and may evaporate, and they are also toxic to breathe. In order to find the rate of flow, or how fast the helium is traveling within a column, you must use a bubble flow meter. Make sure that you have the switch on the GC on the right side. A polar column is the minus, so make sure the switch is flipped on that side. Plug in the tube into the correct column outlet. For the polar column, it is B. Squeeze the bulb until bubbles form in the pipette. Choose one bubble and use the stopwatch to record the time it takes for one bubble to pass 1 milliliter of the pipette. To launch the program on the computer, click Logger Pro on the desktop if the program is not already open. Click File, Open, Not New. Under the Experiments folder, which it's already on, select UMW GC. Do not save any old data. Depending on what column you plan on using, Set the GC polarity switch to the plus for the nonpolar or the minus for the polar column. Use the 0 knob to adjust the millivolt reading on the computer screen to 0.8 to 1. On the GC instrument, record the temperatures and conductivity of the column temperature, the detector, the injector, and the current. Now it's time to load your sample into your syringe. First, rinse your syringe in acetone before loading your sample to make sure to wash out any impurities. Stick the syringe in the flask, pump a couple of times, and then inject into the air. The acetone will evaporate. Now for loading your sample into your syringe, shake up your flask with your mixture. Insert the syringe into your flask, pumping several times and only pulling out the syringe arm about 1 inch to clear out air bubbles. Collect 4 microliters of sample and pull up about 0.2 microliters to get a small amount of air in the syringe. This excess air serves to keep your sample trapped in the syringe so that it does not evaporate before you inject it. If the polarity switch is positive, inject the sample into the non-polar injector port, A. If the polarity switch is negative, inject the sample into the polar ejector port, B. Insert the syringe into the port, pushing as far back without jamming the needle, as this will bend the needle. Once the syringe is as far back as possible, place your finger behind the syringe arm or hand behind the arm to make sure the syringe arm does not fly backwards. Quickly push the syringe arm forward while pressing the start button. So here you can see that we had 3 compounds within our mixture. Right here is the small air peak that we placed in the syringe. Here's compound number 1, compound number 2, and compound number 3. In order to tell which compound is associated with each peak, we need to do data analysis. For your data analysis of your mixture, click Auto Scale Graph. Now click Analyze and go to Peak Integration. In the new window that pops up, click to the left of one of your peaks and drag to the other side. Click Add. Do this for all of your compounds within your mixture. You can rename the compound in this bar here. Click OK when you're done. After your data has been printed, rinse your syringe as demonstrated previously. Make sure to leave the GC the way it is. Do not turn off the gas or the instrument without the permission of the instructor.
Now that you understand how to properly work the GC, you can proceed to run your mixture of compounds. After all the compounds have been fully eluted from the column, you can analyze your results. So that concludes our video. Thank you for watching and good luck on your experiment.